So here we're going to talk about our d orbitals. We'll also bring up our f orbitals in passing. We won't spend much time on the f orbitals simply because they're getting so complex at that point, and they also are atoms that have so many electrons in it. We're going to have a lot of extra interactions going on. That means the complexity is going to increase dramatically for how those interactions are going to behave. And they do still follow the basic rules that we're establishing. Electrons repel each other, and electrons are attracted to protons, and they're all moving around close to the speed of light. But when you have that many things happening simultaneously, patterns can become so complicated that they're hidden, at least to our eye. So we're going to stop pretty much with the d orbital and mention the f orbital in passing. Now this is the shape of the electron probability along the radius of a d orbital. You can see here there's not much chance of finding the electron close in. Out here to about 2 angstroms where we finally start seeing it again. Remember that we have all those inner shells packed in here, and so these electrons are going to be repelled out of that range pretty easily. And they're going to be spending most of their time out here, somewhere around 3 angstroms out to probably about 10 is what I'm typically going to be calling that. That's nothing you have to memorize, but it's good to have a rule of thumb for these things. So keep in mind, these are going to be atoms that are going to be 10 angstroms from radius. That means diameter is going to be about 20 angstroms. These are going to be big atoms. Now, let's see what these orbitals are going to start looking like. In the YZ plane, you can see right here, sitting along the Y and Z axes in the plane, on these diagonals in between the axes lines, we're going to have our DYZ plane. Our next two are going to be very similar. They're going to be identified by the plane that they're in. So we're going to have our DXZ, which will be along the X and Z dimensions. And we're going to have our DXY sitting in the XY plane, again on the diagonals. Now these next two are going to be a bit different. One is going to be right on the axes. The other one is going to be on an axis, but with a very different shape. And that's this one, the DZ squared. The Z squared sits along the Z dimension, and it's going to have one section that looks like a dumbbell sitting along it, almost like a p orbital, but it's going to have this donut shape around it. And this entire thing is one orbital. So that's going to be our fourth shape. And our fifth shape will be the dx squared minus y squared. And if you remember, that's one of our equations for a circle. It's basically going to be sitting along the axes of the xy plane. So it's a lot like these three up here, but it's going to be on the axis instead of in between. And notice that with this one sitting on the axis and these ones sitting on the axis, we end up having all of our axes covered, and we have a spot in between along each of these other dimensions. This is what it's going to look like if we see them all simultaneously. And that's really complicated looking. Well, keep in mind that d orbitals are going to be things that we see for transition metals. And transition metals are going to have lots of extra electrons. We're going to see that when we talk about their properties. Now let's switch over to the orbitron for a moment and take a look at what these look like in 3 dimensions a little bit more. So here in the orbitron we can see the same sort of shapes that we had over on our slides, but also notice that here we've actually added in the shading to show that these yellow ones are going to be sitting along the same axis, and they're going to have the same mathematical sign when it comes to the wave function. So these are going to be lobes that are shared by an electron, and the other electron is going to be focused mostly within the blue, but remember we can have interconversion between those, and the electron can move around because it has the ability to do tunneling, and we don't know where the electron is anyway because of Heisenberg's uncertainty principle and also the de Broglie wavelength of the particle. Here you can see the donut and dumbbell shape, I like to call it. This is going to be a different mathematical sign than the thing that looks like a p orbital sticking up and down. And then all of these others look pretty much like we would expect. So you can see here our f orbital. And we won't get to see our f orbital at all until we have a lot of electrons. We're actually going to have to be in the 4th principal quantum number range before we ever even have f orbitals able to fit in that much space. Now you can see here they're going to have some pretty complicated shapes. You can see it, we have our dumbbell with 2 donuts, another dumbbell with 2 donuts, and another. Here we're going to have a double clover leaf, another and another, and another. So these are going to be really complicated in 3 dimensions. We won't be drawing these at all, but I wanted you to see the next level of complexity with it.